Hello and welcome. Today we're going to be doing an example of a multivariate change of variables. Now let's recall the basic setup. The idea here is that we have a some sort of set, and this set we're going to call D, and it's going to be in the UV plane, like so. We also have some map. It's a function of u and v that outputs a vector in the xy plane that we're more familiar with, like that. That's x and that's y. And the idea here is that if I take a point here, uv, I plug it into this function, it gives me a point out here. And in fact, if I take all the points over here, run them through this function, it'll output some other set like so, called R. Now what we want, the idea here is that our goal is to integrate some function f of x comma y, and we'll call it dA, okay, over some set R. So we want to integrate here. We want to grid that out, say, into a bunch of small little area differentials and integrate over that set and do this. But perhaps it's difficult. And we've seen this, of course, in univariate integration, that sometimes either the domain or something about the function itself, f, make it very difficult to actually integrate it all the way. And the idea is we have a change of variables. Okay, the change of variables here, the idea then is what we need to be able to do is, if I have a little tiny area here, it gets mapped into some sort of zone here, and there's a correspondence between those. But something about integrating the UV plane will actually be easier, and the idea is that it'll be easier to integrate. And of course, not all changes of variables are equal, but the formula for it is if I want to integrate over the region R in the xy plane, the way to do it is to then integrate instead over D, and then we have f, and then we have to change variables to u and v somehow. And then what we have to do then is we're going to have a du, a dv, and then we're going to put a little area distortion factor, which we call the Jacobian. Okay, and that Jacobian is defined as the absolute value of the determinant of the matrix x partial with respect to u, y partial with respect to u, x with respect to v, y with respect to v. We take the absolute value of that. And this represents that distortion that happens. If I take a little square of area over here, which is going to be du dv, and I map it over here, it's going to distort it somewhat. It might expand it, it might make it a strange shape, whatever. If it's small enough, the idea is that there should be some distortion factor between the square here and the square there, and that's accounted for by this Jacobian here. All right, so that's the general theory. Let's go to an example now. Let's go to an example. And I'm actually going to start with an example where, again, I kind of want to think about, this is going to be the UV side, and here's going to be the XY side on this side. And I'm going to put a little dotted line in between the two. And I'm going to be given, on this side, I'm going to start with the region here. The region is going to be everything above the y-axis. In addition to that, it's also going to be bounded by these two parabolas. And the parabolas are x is equal to 1 minus 1/4 y squared, and x is equal to minus 1 plus 1/4 y squared. All right, let's look at what this shape is. Okay, it's going to be, there's the y-axis there. All right, and then there is, oh sorry, this is the x-axis, my apologies. And then there is the y-axis up there. All right, and so when x is 0, that means we have to find a y value that will equal the x is 0 and is also a positive number. And we find that that's going to be 2. And that's true for both of these. In order to make x 0, y has to be 2 up there. All right, and if I come down like that, I want to find out where this crosses. We see if we set y to 0, that this is going to be x equals 1 and minus 1. So we see it comes off like that. It comes down like that. Actually, you know what? I'm going to make this a little bit broader here. So I'm going to say that's an x equals 1, and that's an x minus 1 there. And I'll make it so that the x and y axes aren't perfectly to scale. Okay, all right, so that's my region R. And now over on the UV side, this is clearly a very difficult domain. This is a difficult domain to parameterize. I'm not exactly sure how to do it, but my goal is to integrate the following function. We want to integrate the function over this region, y dx dy. All right, but again, the region itself is what's complicated. So the idea here is we want to find some integral here in the d side, and here we have this UV plane. And we have some domain, which we haven't specified yet. It's now going to be f of x of u comma v, y of u comma v, du dv. All right. Oh, I forgot my most important thing, though. We have to have that Jacobian, du dv. All right. And of course, these two are going to be equal. All right. But now let's see if we can figure out how to do this. So in fact, for this problem, I'm going to give you a given change of variables. And here is the change of variables. We're going to say that the change of variables in this particular case is going to be u squared minus v squared, comma, 2uv. And that's going to be my x of u comma v, y u comma v. That's my vector function. Okay, so this is good. Let's calculate our Jacobian really quick. Okay, so we know that the absolute value of the Jacobian is going to be the determinant of the x function, partial derivative of x with respect to u, which is going to be 2u. Okay, and we know the partial derivative of the y function with respect to u is going to be 2v, because when we take the derivative of this with respect to u, 2v is the constant that sits out front. Now we do the same thing for v. We take the partial of x with respect to v, we get minus 2v, and then finally here we take the partial of y with respect to v, we get 2u. All right. Now let's take that determinant. We get a 4u squared plus 4v squared. And that becomes 4 out front, u squared plus v squared. Okay. Right, again, this is our given change of variables. We didn't have to come up with it. It was given to us in the problem. And now we've computed that area distortion factor. All right, and in this case, it's always positive, so we can drop the absolute value signs there. The question then is, we still have this question is, what is the domain D in the U of V plane? So that when I take my function R, this is that vector function R of U and V. Sorry, that should be a vector. So when I take every point over here in the UV plane, it produces R over here in the XY plane. Okay, for that we're going to have to do a little bit of, maybe do a little bit of effort. So let's move to a new page. Again, I'm going to have to write some of my facts down again. What I had was, I'm going to try to, again, keep the correspondence here, XY on this side. We had 1 out there, 2 up there, a -1 that is. Okay, and that function was -1 plus 1/4 y squared equals x. Okay, that was this side right here. And then this side on the other goes in there, and it is 1 minus 1/4 y squared is equal to x. And of course down here, that is equal to, that's the y equals 0 line. So those are the lines that border, these curves border my, my set R. Okay, over here in the UV plane, again, we still have the question mark. What set over here? The set is, we don't know what D is. So that when I take my vector function and I plug in values for U and V, I can produce this whole strange set over here. We have our function. The function is U squared minus V squared, comma, 2UV is equal to X comma Y. Oops. All right. And what we want to do now is really examine these curves over here and see if I can make a correspondence between these using this function. So the first one I want to look at is y equals 0. Okay, so the y equals 0 line, how do I get that? So we see right here, immediately we have a y equals 2uv. So the question is, so if this is now equal to 0, so this is on the y equals 0 line, so I'm down here, what does that correspond to? How many ways are there in the UV plane to make y equals 0? So clearly, there's many, many ways to do it. So there's actually several ways to do it. We see here that if u is 0, then y is 0, and if v is 0, y is 0. So we know that, I'm going to just draw this here, we know that anything here can get you, anything along these lines here is allowable. Okay, so we know that the answer then is if u is equal to 0 or v is equal to 0. That will deliver that perfectly. All right, so we want to know exactly what sections of these lines here I need. These are going to be borders to the set, we know somehow. Okay. All right, so we have that, but we still don't know much. We just know that we're along these lines, and we're along these lines on these axes. The next thing, though, is we need to figure out, we want to look at these curves up here. Okay, so I'm going to start with this one over here. So if I start down there at the y equals 0 line, and I want to move up on this curve, first of all, I know in this case y is equal to 0, so u or v have to be equal to 0. And that means the y will be equal to 0, and x will be equal to what? That means if I put this, if I put y equals 0 in here, if I'm right there at that point, then x is going to have to be equal to 1. Okay, so x is going to be equal to 1. Is there a way to do that? If I look at this function, this will be 0 here, because that's y, right? And then, and again, this is the same thing as on the y equals 0 line. But I want x to be equal to 1, and that occurs in which case, this x equals 1 when u is equal to 1. All right? And v is equal to 0. That's a good way to do this. All right, so now I know that if v is equal to 0, and then u is equal to 1, this point right here corresponds to that point right there. So I'm actually going to put a little square around that to indicate those 2 points correspond. And anything on this line here corresponds to stuff going up to it. So I'm going to put an arrow, 2 arrows there, and 2 arrows there. Now we want to check when u and v both equal 0, what point do we get? That's 0, and that's 0. And so this point right here, I'm going to give that one a star. Those points correspond. Okay? Sorry, I should do a better star. One that's a little bit more easy to see. So those points correspond, and you go between those lines there. All right, so now we have that we can call this one, I'm going to even call this S1. I'm going to call that S1. All right, now, if the opposite occurs, I want to go out to this point. And this is the point (-1, 0). All right, well, if I'm on this line, I know that y is equal to 0 again. So this is 0 here. How do I get here? How do I make that a (-1)? Well, that means v has to be 1 and u has to be 0. And so I have to go up this way. If I go to this point right here at v is equal to 1, that corresponds to this point there. I'm going to give that one a triangle. I'm going to give that a triangle right there. So I'm going to call that side 2. I'm going to call that side 2. So now we have a correspondence between these borders. And this is strange because this is a straight line, but this became a it has a bend in it, actually. So that's an interesting aspect of this map. All right, so we're seeing the outlines of maybe a square, possibly, but we don't know yet. We still have to figure out what happens to these curves here. All right, so let's see if we can do this. So let's start here. Let's start here. We have this this curve here, like that. All right, we know on this curve that both u and v aren't going to be 0. So we can actually say that, so now let's look on the 1 minus 1/4 y squared equals x line. Okay. We know that also that y is equal to 2uv. All right, and then so we can actually solve for we know that u is equal to 1 at this point at the start, and it's who knows what it's going to be up here. But what we can do then is actually just solve for v. So we can, but we know that it has to, that u, at least from here, from this point here, that u has to be 1, right? So we don't know what's going to happen to u later on. So let's see if we can solve, we can start at this point, we can go that y over 2u is equal to v. Okay, so that's nice. And what we can do then, because we can actually plug that into the other side, we know that 1 minus 1/4 y squared is equal to x, and x is equal to u squared minus v squared. Okay. So here, what I want to do now is actually plug this in for v. So we have u squared minus y squared over 4, because we're squaring, u squared. All right, so these two things have to be equal along this line. And the only way that happens, we conclude then that u has to be equal to 1 for the entirety of that curve. We know it was that u was 1 at the beginning, but we found out it's actually true along this whole curve. So in fact, u is going to go up like that. Like that. And those correspond like this. Okay. Now the question then is, on this line, if u is equal to 1, that means that y, so u is equal to 1 everywhere along this line here, and everywhere along that line there. So what is y equal to? Well, y is equal to 2v. Okay, so when do we stop v? We want to stop, y is going to terminate here because that is actually y equals 2 right there. We know that v has to terminate. So v equals 1 is this top point here. So that point there. So we've done star, we've done square, we've done triangle, so I'm going to do an open circle there. And that goes across there, and that represents circle. Okay? And I'm going to call this side 3, and that's going to correspond to side 3 there. You could probably figure out additionally then the length there has to be here. So that I'm going to call side 4, and that is side 4. Okay, so my D then is this set, which is going to be, I can write it down then I conclude that D is this set in the UV plane equal to, it's just the unit square. Like so. So that's my D. And we have our Jacobian. So now we can start with our integration. So now we have this set D, and when I plug it, put it into my map, I can get my R out. And clearly this is a much easier set to integrate, because it's a square, and that's a much simpler set to set up an iterated integral for. All right, so now let's go and do it. Let's recall again what we had. We had our goal was to integrate over R of y dx dy, okay? And we know that my Jacobian was equal to 4 u squared plus v squared. That was it. And we know my set D then is equal to u comma v like so. And so we can put this all together that this is going to be over D. And now y, what is y? Y is equal to what now? We said it was 2uv. That was from our map. From R, u comma v equal to u squared minus v squared, comma 2uv. Okay? So we knew that that was true. So I can actually put that in, 2uv, okay, times, and now I have to put in our Jacobian for u squared plus v squared, all quantity there, du dv. All right, so I'm going to move this down here, keep going, and I know to do the iterated integral, I go 0 to 1, 0 to 1, and now all I have to do is, I see there's a 4 and a 2, I'm going to turn that into an 8, put it out front, and then that's going to become a u to the third times v plus v to the third times u du dv. Okay, so this should be straightforward enough. Let's do, and that's the integrand there. 8 So now we have a u to the fourth over 4 times v plus v to the third u squared over 2. We're going to evaluate that at 0 to 1 dv. I'm going to factor out a 2, so that becomes a 4. And then we have 1/2 v plus v to the third power. Yeah, that's it. dv. All right, we're looking good. And now finally, 4. We have a 1 over 4 now, v squared plus v to the fourth over 4. Evaluated at 0 and 1, and we can compute that to then be, okay, that'll be 4 times the quantity 1/4 plus 1/4. Okay, otherwise known as 4 times 2/4 is equal to 2. All right, and that's the answer for that problem. All right, I hope you enjoyed this, and I hope you found, let's maybe talk briefly about it, the idea that, what was the challenge here? I think the challenge was finding d. That was the challenge in this case. The actual integration was fairly straightforward. All you have to do is use the formula. And so finding d might be the challenge. In other cases, actually finding our actual r function, finding it might be hard. That might be difficult. And also, computing the Jacobian, finding d. So there are other cases the challenges can show up in different places. It may be sometimes that the actual finding of d is actually fairly straightforward. It's just finding out how to do the substitution that's hard. And it could, in other cases, even integration itself. That can also be hard. And either way, though, the idea is that change of variables can work to alleviate some difficulties in some aspects of multivariate integration if you choose the right substitution in order to simplify your problem. So I hope this helps. Thank you very much.